All right, we are back. Everybody have a good break? Okay, so enough of this fancy-dancy statistical stuff. We're going to actually, there's the part in R. We're going to actually talk about some performance, and then we're going to go and guess what? We're going to test some more web pages. All right, so let's get started. This is operational research section. Disclaimer, nobody really knows about this in the performance world. When I first started doing performance work, I had known about this because as a mathematician, I was just fascinated by it. It's like, whoa, I can actually figure out how hamburgers come out of McDonald's and figure out how long it's going to take. And I was pretty fascinated. But when I got to doing performance work, nobody was using any of this good stuff. It all came out of World War II. And, you know, I think we've all seen those articles about World War II, and they say, oh, we turned out a new airplane every 5 minutes and a new boat every 5 seconds, and so on and so forth. And they've got these amazing supply chains building all these war machines. How in the world could you run a supply chain like that? Well, they came up with, through this idea called operational research, they actually found a way to use mathematics to characterize what happens when people line up to do things and want to do things in order. And we call that operational research. It's a set of rules. Sometimes, I mean, throughout we'll call them laws, right? The force flow law, the utilization law, Little's law, response time law is actually the most important of these, right? But when I say law here, I'm using it lightly. This has nothing to do with Congress, and it has nothing to do with gravity. These are just observed empirical rules. So don't attach the same weight to them as, you know, the laws of the universe, whatever those are, right? These are things that we've learned by experience of dealing with large systems with lots of moving parts. We're going to derive the response time law, but before I do that, I want to give you an idea of why it matters and why I'm standing up here babbling about it when I could be talking about GIFs or CSS or JavaScript performance. This is the really important part. Queuing theory. There's only 3 things you need to know about a queue. Right? So you're standing in line at the movies, you're standing in line at McDonald's, we stand in line all day. Right? For various things, we get in line when we're on the freeway. The freeway is a big queue, right? It's parameterized in terms of freeway exits. I mean, you can't really get off or on anyplace else, right? It's a big queuing problem. And actually, if you apply the rules of queuing theory, it'll get you to your destination more quickly on the freeway. But that's really geeky, and I'm not going to go into that right now. The 3 things that you need to know about a queue are, so let's pick an example. We're going to stand at the movie theater and get our tickets. Right? So the 3 things that you need to know is how long does it take for the person to punch up a ticket and give it to you? Right? That's going to be important for how long people have to stand in line. Right? The queue residence time. That's exactly it. How long do you have to stand in line? And then there's the queue length. How many people are standing in line? Right? So if we think about this queue, there's an arrival rate. People show up and they go and stand in line waiting for their tickets, and over here somebody processes their ticket, sends them on. We've got a queue. The residence time, how long you stand in line. Queue length, how many people are standing in line. So-called service time is how long it takes you to go through that process. When we're talking about requests coming into a website, it works exactly the same way. They get queued up, processed in the order that they're intended to be processed. There's some subtleties here. If all of the request doesn't arrive immediately, the server will wait for the entirety of the request to arrive, things like that. But in general, these things can be modeled as a queue. First come, first served. How many people are waiting in line helps you determine how long it's going to take that web page to show up, right? Because not only do you have to wait for the server to do its thing, you also have to figure out how long you're going to stand in line. So if you want to know, back to our movie example, how long is it going to take me to do my ticket, or to get my ticket? What do I need to know? I'm going to count the noses, how many people are in line. I'm going to count how long it takes for an individual to get his ticket, and then I'm going to know my queue residence time, how long I have to stand in line. And a lot of times, if you live in the valley and it's on Sunday, you go to the restaurant and you look at the queue length and you say, I'm going someplace else for brunch. Anybody had that experience? Seems to happen to me every Sunday, right? We're good at estimating queue length and estimating the response times for queues. People are very good at this because we have a lot of experience with it. You can take that intuition and apply it to your web page. So all these systems are just big queues, and they have some utilization around them, right? Now, obviously, what we want to do is keep the pipe full, right? Anytime that the pipe isn't full, the cashier at our movie house is standing there twiddling her fingers waiting for somebody to show up and buy a ticket, right? Wasted money. You're paying that person. You're paying the servers to sit around at the same time. How do we tell what the utilization is? Very simple. It's the fraction of the time the resource is busy. We've got some average throughput for the queue that say, oh, we handle 15 people per hour. We can get 15 people tickets per hour. And then we know the average service time takes, 1 minute to get a ticket or whatever. Utilization law is very simple. It's just the product of those two numbers. This is just, I'm building toward the response time law here. The utilization law is not necessarily directly important for performance work. It's very, very important for capacity planning, which indirectly obviously has a huge effect on performance. So don't lose the utilization law. But in the class, we're really going to spend more time on the response time law. And here it is. So I could have typed all of this good stuff into PowerPoint and tried to do it, but I decided not to. I basically stole Professor Jane's slide on this. And so we're going to use his slide for the response time law. This is really the interactive response time law. Remember I said earlier I was starting to think a lot more about the engineering psychology that goes into performance and what the user is doing as the client in this thing, right? It's not just about server, it's not just about the network or even the browser, but about the user. What we talk about here is server duration, right? That's the service time that we talked about. How long does it take the server to process your request? And then we have the client think time, which is the time it takes the client to respond to whatever you sent to them and take the next action. On PayPal, for instance, when you make a PayPal payment, there's 3 steps: login, review, confirm. We want to get you through those steps as fast as possible. So we try to reduce the amount of think time necessary on your part to get through that process. Because if you have to think about it, what's my login? What's my password? Is it really the same as my Yahoo Mail? I don't think so. Maybe it's the one I use for Google Mail. If you have to go through that long think time process, obviously the process appears slow to you, whether PayPal delivered stuff on time or not, right? We want to minimize the think time. So we do things like we save your ID. So all you have to do is type in your password, or we leave you logged in. All these are ways of reducing the necessity for the user think time. If you go back to that engineering psychology book by Wickens, he talks about 3 things that are important for human performance. Response time. Yes, he actually says response time, right? Accuracy, right? And cognitive load. The think time is about cognitive load. How long does it take for me to respond to whatever the user or the server sent to me? It's not just about how long did it take the server to send stuff to you, but also how long it took you to respond to the server. There's a conversation going on here. The interactive response time law takes into account the user's think time, assumes it's non-zero. A lot of representations, if you go read books on web performance, they always assume the user acts instantaneously and doesn't have to think about anything, right? We need to use the interactive response time law. So very simply, if Z is the think time, R is the response time, the total cycle time for the request is the sum of those two. Everybody with me so far, right? Each user generates about that many requests in some time t. It's all pretty straightforward. So if there's end users, and we're going to do a little exercise on this because I know it's sort of, I'm going through it in a brief way, and it's hard to explain mathematics from a PowerPoint slide. It's just hard, right? So if there's end users, we go through a little bit of algebra here, and I'm not going to go through it. I want you to see it, right? We're calculating the value of x, right? And total number of requests divided by total time, that's the average throughput. Right? Very simple. Number of requests. We end up solve for R. Remember, Z is the user's think time, and that's the response time law. What that tells you is, given a system with that level of throughput and that many users, that's going to be the response time. Now, does it work? Can I plug Google's response time into the response time law and get anything? Well, I don't really know much about users' think time. That probably varies on an individual, right? But what if I plug the numbers in? What actually happens, right? So this is a nice little academic thing. I stole it from some professor. Let's do a little bit of hands-on. with the response time law and see if it works. Right, so we're going to do Facebook. Everybody liked anything? Who in here has never pressed a like button? Oh, all right, yeah, I believe you. I totally believe you. Not. So let's say Facebook's web servers can process 10K like requests in a second. That's our throughput. Remember from our previous slide, right? And the number of concurrent users is 600K, which probably is a bad day for Facebook, right? But, and you know, those requests are coming in every 5 seconds. So every 5 seconds you're liking something, right? Bing, bing, you know, I like potato chips and Coke and whatever it is. So how long is it going to take? What's the response time? So this is a hands-on exercise. That means you actually get out your hands and plug the numbers in and you tell me what the result that you got was. Just if I have to explain these things. So the formula is here on this page. I didn't want to have to flip back and forth between slides. So what's N? So N is the number of users, so it's what, 600,000 in this example, right? So what's Z? Right, so it's 500 or 5,000 milliseconds, 5 seconds, right? So we know what X is, X the throughput, right? And it's 10K requests per second. We're not even doing algebra here, guys. This is just arithmetic. So who's got the answer? So we know what the value of Z is. It's 5 seconds. Now I very clearly set this example up. All the numbers are here for everybody to solve it. It's not, there's no tricks, or it's not a trick question like when I drew the graph incorrectly. Right, this is very straightforward. So who's got an answer? All right, so hold that thought. I want to get a couple more people and see if we can get some intercorrelator agreement between people calculating the numbers. So you got a number? So you get a number? Okay. Who's got a number? All right, very good. Most of the people. So what did you get? What did you get? Okay. So sounds like we have at least some agreement around 55 milliseconds. So I set it up so the numbers would come out pretty even, right? It would be a pretty round number when it came out. So we see where this came from. You see where this came from? So what I find is that this is not the greatest demo for a class, simply because everybody gets it wrong. And I've done this several times when people have not been able to calculate it. So in some sense, you can regard it as a trick question. You have to be able to run the numbers and run the formula, right? You got to account for the conversion factors between milliseconds and so forth. But this is the answer, and it was sort of set up this way just so it would come out to 1,000 milliseconds. If I click on a like button, let's say I'm going to like Burger King, right? And it takes a second for the little icon to change, right? Because that's what happens when you do a like, right? What do I think when it takes a full second? Huh?
Did it go?
Yeah, yeah. About 600 milliseconds in, I'm wondering, maybe I ought to click it again. Maybe it didn't hear me the first time, right? I mean, do you guys, so I find I do this a lot. When something is slow, I click it again, wondering if it heard me the first time. Do you guys do that a lot? Yeah, of course it did hear you the first time, right? This is an underlying performance problem. When we get to the T1 segment of the model, I'll explain why that's so important and what you can do about it. Not much, unfortunately, but there's some things. But anyway, the response time law works. And the Facebook guys actually looked at this. I had a guy from Facebook in the class last year. He actually came in. He was like somebody I had known for a long time, and none of this was a mystery to him. But he came in and he went and actually tested his like times right in the class while we were sitting here doing it. And it wasn't anything like 1,000 seconds, but he said, oh yeah, I guess we do need more servers. And he was getting like 55 milliseconds or something. They have pretty high standards. But it did result in some thinking. Sir?
Is this assuming that all 600,000 users are doing a like every 5 seconds?
Yeah. Now that's a little bit idealized. We don't just sit here in herds of 600,000 each and type like, right? But we know that we have an average throughput number for our website, right? And that's all we need to know. If we want to calculate these things over the period of an hour or a day, it doesn't really matter. All we need is the average throughput over that period. Now, we do have secular cycles. Everybody, I think, understands that just like the freeway, the internet is more congested at times of high usage, right? So when you get on the freeway in the morning, everything is slow because there's a lot of cars out there, right? And the capacity of the freeway is being used by all those cars. Websites the same way. If you look at Yahoo's traffic patterns, gets to be lunchtime, boy, everybody checks their mail. And then it goes back down to some average value. About 2 in the morning, it goes down to its minimum value. And it goes through this secular cycle. And actually, the traffic patterns follow the sun. And that's not really amazing. We're daylight creatures, right? We kind of expect to do that. But we have these secular cycles. And what you see in Facebook's instance, for instance, when they're doing likes, is that at 2 a.m., a like might take 55 milliseconds, but at noon, that like may take 1,000 milliseconds. So now what do? Right? At peak time, you have a lot of congestion, your website is slow. At average times, your response times are okay. What do? Facebook needs more servers. Right? I mean, there's not much you can do about the freeway being crowded, but you can have enough capacity so that the people have a place to park once they get off the freeway, right? It's like, you can't change the secular cycle. People are going to go and check their mail at noon, and they're going to crowd the existing bandwidth, right? There's 2 things you can do. You can add bandwidth, right? That's not necessarily easy or cheap. You can try to make your property appeal to people at off-peak hours. Some people do that, right? Off-peak doesn't mean the same thing for everybody, right? What's Netflix peak time? Anybody know? It's about 7 or 8, right? And rumor has it, and I've never been able to track this number down, but rumor has it that they're responsible for about 30% of capacity at peak times in the evenings in the US. I'm getting the feeling, though, that number, that 30% number, is actually an urban legend, because I have not been able to actually track down a source for it. When I went and asked the guy that used to be the chief architect over at Netflix, he didn't know about that number either. So I think it's an urban legend. But they do operate, they do take up a lot of capacity at peak time. That is not necessarily peak time for Yahoo or Google, though, right? Peak time varies. Anyway, I wanted to, throughout the talk, I have several anti-patterns that I want to point out to you. I used to do this in terms of, 7 principles of performance. I got bored with that because I've given this talk so many times that I decided to take a different approach and talk about anti-patterns and just sort of invert the thinking. So the first anti-pattern of the day, keyhole optimization. Optimizing your project in such a way that my project sucks. And that happens a lot, man. What I see is developers doing is they're like, the database is slow. I'm going to run multiple parallel queries at the same time. Of course, somebody else trying to make a query at the same time is sitting there struggling, right? And I see people do this all the time. They don't think about the system. They don't think about the end-to-end. And this costs you in 2 ways. One, you might over-optimize something at the expense of something else. The other way that it's really bad for you is that you might actually not or miss the opportunity to optimize something that's important, right? The third really important reason that you want to think about the keyhole anti-pattern is that you're going to find that you have rocks in your lawn. So what do you do when you have a rock in your lawn? You can't move that rock. What do? You mow around it. Right? What are you going to do? You compensate for whatever obstacle is in your way. It's the same way with web performance. It may be that database call that you're making can't be reduced in its response time. You can't make it any shorter. It's already been optimized. They've done their best. The database is running as fast as it can. Steam's coming out of it. You're not going to be able to optimize that. By understanding the whole system, not doing your keyhole optimization, by understanding that whole system, you might be able to find someplace else in the E2E where you can compensate for that rock in your lawn. Right? That database call takes forever? Fine. There's nothing I can do about that database call. I'm going to go make this other part of the end-to-end go a lot faster just to make up for this slow section. Right? If you have a rock in your lawn, you got to mow around it. Right? Pay attention to the whole system. It's not just about what you can see. One problem I have at PayPal is that PayPal's website's essentially a utility. Nobody really goes to the website except to add an account or change their password. You know, it's a utility website. I don't want people going there. Most of the traffic goes over some API, right? But when I talk about performance of the APIs, nobody wants to hear about it because nobody's ever seen one. Right? But they want to talk about the web page performance because it's physical and they can see it. Oh, look, you know, it's fast, right? Whereas you can't see an API call. Don't just pay attention to what's inside your scope of vision. It's a system. All right, so this is the fun part. We are done. We are done with all the statistics and the background and all the academic stuff. Now we're going to talk about the performance. I hope that everybody is up to speed and has learned something so far about how we're going to go through the rest of this. Mount Fuji again, approaching summer, flowers are in bloom. The MPPC model, multiple parallel persistent connections. We'll get to that part. So what affects the response time? When I go to load Google, what factors affect this? So geography. It matters a lot. If I'm in Lithuania or if I'm in, you know, Palo Alto, my response times are going to be vastly different, right? Network location. This is very different from geographical location. Maybe I'm sitting in the office of a Silicon Valley Fortune 100 company that has, you know, pipelines up the butt, right? Network location. Some guy 5 blocks down the street, same geographic location, may be still running on some 9600 baud modem. Network location important as well. Bandwidth, the whole thing is about bandwidth, except when it's about latency, and we'll talk about that shortly. These are both network effects. No user, remember, ever experiences either bandwidth or latency. They experience response times. But the underlying bandwidth of the network, big deal for performance, up to a point. Transport type, it matters a lot whether you're going over Wi-Fi or your phone or your Arduino or your Raspberry Pi or your big Digital Tigers multi-CPU, you know, warhorse. It matters what the transport type is. It matters what the browser and device type is. People often ask me, you know, in the days of evergreen browsers and people optimizing the crap out of V8 and so forth, does the browser still matter? I can show you test cases. Remember, I do a bunch of work at the W3C, so I see all the test cases. I can show you test cases of 2 browsers, and I won't mention which ones, but they're both located right down the road here, right, which would tell you, right? Both of those browsers running the same page, 50% difference in response time. Right? It matters a lot. I was amazed by that. Normally browser differences, plus or minus 10% in most cases. Normally almost always in either the layout engine or the JavaScript interpreter. And I marked the 50% for the browser change. The page composition. So if you read Steve Sauter's books, he's all about page composition. How do you construct your pages to make them fast? And that's very useful information. It's just not the whole story for performance. There's a lot more that goes into it. Things like bandwidth, transport type, etc. don't just pay attention to the page composition. The reason people pay more attention to the page composition is because you can put your hand on it very easily, whereas if you have a problem with your DNS server, it's going to be a little bit harder to fix, right? That doesn't mean it's important. If you only get 1% improvement changing the page composition, then it might not be worth doing, right? We'll talk about how you figure that out on the 3 slides from now. Network transport effects obviously have a big deal, right? The wireless system in Starbucks, and I don't know if anybody has noticed this. So first off, they're using 802.11b, which is, somewhere back in the dinosaur days as far as wireless is concerned. The other thing is that it's artificially limited. So normally 802.11b is limited or supposed to be limited at about 10 kilobytes. Starbucks has artificially limited the bandwidth on their wireless networks inside their stores to about 4,500 or 40.5K. Why they've done that, I don't know exactly. They probably had problems at the high end with people hogging bandwidth. So they artificially limit it. That's what I mean by network transport effects. Obviously, the number of connections, whether you use a CDN, these are the 14 so-called Y-slow rules. The disclaimer, it was my group at Yahoo that came up with those. Those are the things that have an effect on performance. And I didn't mention a few of the others, or at least I didn't go into details about JavaScript engines and things like that. There's other things that affect it. Those are the main factors. So what happens in your house when you make an HTTP request, right? I think most of you guys already know all this good stuff, but I'm going to go over it briefly. But I do run into cases where people really don't understand it very well, and it's useful to go over it. So just at a purely physical level, let's look at what an HTTP request response cycle looks like. So the first thing is your home, which is right there. And here's your PC, and it has an Ethernet card or a wireless card, amazingly enough. Goes out to a home router, probably a cable modem, something like that. This is all in your house. It's your responsibility to keep this stuff running. And because you don't, not you personally, but because most people manage their home networks poorly, we have very bad response times in people's homes. The drop-off of response time from the last ISP point of presence, called the terminal point of presence for the ISP, and the person's home PC is often about 50%. And you'll see this in the commercial tools. If you use CompuWare Gomez, or if you use Keynote, one of these tools, they call backbone and last mile measurements, right? Last mile is often twice what the backbone measurements are. Why? I mean, it's all cable. I was talking about this to somebody when I was outside on the break. The cable that goes into my home is pure fiber, right? It goes all the way out to the ISP's point of presence and all the way through and around and up and down. Every single segment, all fiber, all cable. Why does the response time drop off 50% across the system boundary? Well, part of the reason is because all this stuff is managed by somebody who gets paid, and paid pretty well, to actually manage it and make sure it runs continuously. Whereas the person who runs your home network is miserable, overworked, undertrained, and basically oppressed, right? How many of you people do a great job of managing your home network? I mean, I have like 18 routers in my house and switches, and you would not believe my cable closet, right? And I don't manage all that crap nearly as well as I should. Now, okay, admittedly, I'm a special case, right? But when you pop up your phone and you look around, how many wireless networks named Links's can you find just standing here right now? Right? People don't manage their home networks very well. This is a huge response time problem. It's called the last mile problem. Be that as it may, the data goes over the cable modem, goes out to the ISP's point of presence, and they've got some things going on here. Primarily, the most important one is they've got a DNS server. And this allows you to resolve most DNS queries at the ISP's point of presence rather than doing an authoritative lookup. We'll talk more about DNS shortly, but Once we've done the DNS lookup, and let's assume that it was cached there, then we go out to an internet exchange point. This is basically a huge data center. It's usually run by the large-scale ISPs, Sprint, AT&T, people like this, huge 45 megabit cable trunk lines. This is where your BGP happens. This is actually a method of using DNS for availability. The big honking data center, right, big junction on the internet freeway here, and then your request goes out and it might go to the CDN, Akamai, gather some static assets. Somewhere there's a web server, google.com, twitter.com, and of course it's got all this good stuff on it. The web server may or may not be in a colocation center. Some people only run proxies in colos, other people have dozens of colos of their own. Some people rent space in a colo from Amazon, other folks don't. It kind of depends. But just to get the idea of the hardware path, PC, home router, cable modem, out to the ISP, off to the big backbone node here, off to the web server, possibly a stop on at the CDN. So that's nice. That's the hardware level. Let's dig a little bit into the software level. Now, how many people have seen the OSI stack? Please tell me. Okay, maybe not. Okay, all right, so I'm gonna go through it a little bit here. The OSI stack came out of some thinking in the 80s, basically about how networks work. When TCP and things like this were being developed, we really needed a good model for this. Microsoft was trying to take over the Ethernet space by promoting their Ethernet or EtherType 2, and we needed a model for this. So we have the OSI model. It's basically a mental structure that we use for ordering the network stack. And we're going to go over it in a little bit of detail here. And 7 layers in the OSI stack. Yes, this really does matter for performance. First layer is the physical layer. We just talked about all that, right? Cable modems, stuff like this. All this operates at the physical level. Here we don't have bits or packets or messages. We've got voltages. Second layer is the data link layer. You don't worry too much about this. This is where Etherlink lives. The little cable that you plug into the back of your machine fundamentally talks a standard that talks here, but it's not important either. For performance purposes, we really care mostly about this stuff. The network and transport layers, this is where TCP and IP live. Does anybody see anything wrong with the diagram? You probably won't see it here because you probably can't read it because the text is very small. But I stole this picture, as I steal most of my pictures, from somebody on Google, or on Google Images, and I didn't bother to credit this person for their picture. Now normally if you've seen on all these other slides, I credit people when they do good work and whatnot. This person's picture was wrong, so I took the credit off. I'm not going to give you credit for getting it wrong. I mean, seriously. So you'll see here that this person has marked SSL and TLS as being part of the transport layer. Bing! Not true. SSL lives up here on the session layer, well above transport. This is TCP IP. This is all packets. You get up to here, we add encryption. We get up to here and we can start talking about what GIFs look like. Right? What's the format for a GIF? What's the format for a JPEG? At the very top of the stack is where our friends live. HTTP, HTML, things like this. At the very top, users interact with applications. This stuff is all supposed to be hidden from you, and unless you're a geek, you should never see anything below here. The whole point of the structure of the stack is that you don't have to worry about anything below it. It's all hidden from you. A good example is in HTTP 2, right? So if you go read about HTTP 2, the forthcoming version of HTTP, the first thing you'll find is somebody from Google telling you that HTTP 2 is trying to fix latency problems, right? But you can look here at the OSI stack and see immediately that that's not the case, right? Because HTTP lives here on the application level, and TCP IP, where packets live, where latency occurs, happens here. Nothing that you do up here is going to make anything faster down here. Now, things that you do down here can certainly change the effects upward, but not downward. And you may not even know that there's such a thing as packets. There's no need for you to know about that, right? What I want you to take away from this is that A, latency happens here, and no user ever is down here. Users are up here, so it's not about latency. The second thing is that for most purposes, for performance, you don't care about anything but these transport, session, presentation, and application. And honestly, you really don't care too much about the presentation layer because these are normally applied to fixed formats that, you know, there's some piece of software that encodes and decodes it, right? MPEGs and GIFs and so on, right? You don't really care too much about layer 6. There's cases where you do, but not for performance purposes. Mostly what you care about is here, here, and here. And you really only care about this because of SSL. Anybody looked at SSL or SSL performance? So is SSL slow?
There is a controversy with that, but
oh, I didn't ask you if there was a controversy. I asked you if it was slow.
that's just a necessary evil because we can do this obviously.
So I ask people this question all the time because he's right. There is a controversy, right? It's like if you go ask the Google guys, is SSL slow? And I did this. I asked Adam Langley, right? And of course, I got weasel words, just like I got weasel words, right? SSL is not computationally intensive, right? Oh, and that's nice. You're right. It's not computationally intensive, especially if you're Google, right? But SSL is slow. And I have data to show you this. And the Google guys have data to show you on this too. They're not showing it to you because nobody shows their performance numbers, right? But SSL is slow. And I may be unique among my colleagues in that I'm willing to stand up here and say that SSL is slow publicly. And the reason I can do that is because I don't run a browser, I don't run a data center, and I depend heavily on SSL to get my job done. Every connection to PayPal uses a 2048-bit EV certificate and takes a hell of a long time to do the SSL connection. SSL is slow, so that layer 5 is a big deal. Just trying to put some sense around it because I know that that brightly colored image and the text is not the most readable thing. I actually made some readable slides about the OSI stack. Just very simply, we've got bits, we've got frames, we've got packets, we've got organizing the packets for flow control, we've got sessions, we've got images and basic binary data formats, and then we've actually got applications that do things with all those services below them. Right? A little mnemonic for that. Right? Application, presentation, blah, blah. Right? Anybody take an astronomy class? Do you remember the mnemonic they taught you for the star classes, right? Oh, be a fine, what is it? Oh, be a fine girl, kiss me right now. It's like O-B-A-F, right, for the star sequences. Same sort of thing. We've got these mnemonics for this. And this is the one I hear more often. I've heard a couple other mnemonics for remembering the OSI stack, but I can't really repeat them in mixed company. So we're going to stick with this one. All right. You've seen that my method is to start at the top and focus downward, right? We started with the systemic qualities, we went down to the manifest qualities, and we looked at performance, we looked at the hardware, we went very high through the OSI stack. Now we're going to focus down on what happens with our best friend HTTP. So, the HTTP connection flow, the first thing that you want to know is that HTTP is just simply request and response. Not every protocol, obviously, is a request-response protocol. There's some assumptions we make about request-response protocols, right? For instance, that the request and the response aren't going to take very long, right? If the response can take an hour, right, it is not a good candidate for a request-response cycle. It's a batch system. Right? If the request response cycle goes by in a couple milliseconds, right, it's probably not a good model for a request response system either, right? Because request response is actually a fairly slow pattern. And if you can move that fast, you probably don't want to use it. Request response only fits certain cases, right? when we actually make a connection onto a web server, and that's a complicated process, there can be as many as 13 round trips creating an HTTP connection, believe it or not. When we do that, we go through a very simple set of steps here, right? So we do a handshake, we send a request, the request goes in, and you can see that here, right? So this is the server, and this is the client. I shouldn't assume people know sequence diagrams. Just I'm so used to looking at them, I just assume everybody knows what they are. But basically, these are two system boundaries and messages passing between them, right? So we do a little bit of connection setup. There's some other things that have to happen there. We'll go into detail. A request is sent. The server, this is our server duration here, remember from our queuing thing, right? And then we have Z, the client think time, right? So this sequence diagram actually takes both the server duration and the client think time into account. And we've got these messages going back and forth. Our whole goal for all of this, make these lines shorter. That's it, right? Including the think time ones.
Danny,
Sir?
do you mind if I ask a question? So, I think part of my confusion about your definition of terms is the difference between latency time and response time. Because I would call that diagram the latency diagram.
Really?
Well, there's a processing time too for the response, and then the user sees whatever they were supposed to see, the homepage of twitter.com loading, for instance. So I've seen definitions where the response time is the processing time plus the latency time.
And that's probably true if you're a CPU, right? It just neglects the network time, right? So hold that thought just for a second, because I think I'm going to answer it right now. All right? No, you're doing the good thinking. You just haven't gotten there yet. So, and that's okay. That's why you're here. So this is the slide. I've used this same slide to explain the MPPC model now since 2009. And I don't think I fundamentally changed the slide very much. I probably should at some point. I think it's actually in the book as well. So this is actually a request and a response cycle, and this is the whole thing, what we call the E to E, the end-to-end, and all the various steps. And I divide the whole thing up into 4 time segments, and I call them T1, T2, T3, and T4. Not very exciting names, right? T1 is the connection time, T2 is the server duration, T3 is the transport time, and T4 is the rendering time. And the rendering time is, we'll get into a little bit of detail about that because there's some more things that happen there, not just rendering. So I divide my time sequence, or my end-to-end, into 4 time sequences, and then I find out how much time I spend in each bucket, right, as a proportion of the overall end-to-end, and then I go fix those problems first. There you have it. That's it. Are we done? No, I guess not. Seriously, that's the basis for the MPPC model. There's an enormous amount of empirical and mathematical background. I'm not going to bother you with that here, but the basic idea, there's 4 separate steps. These first 3 are linearly independent terms, span a vector space. T4 is not. Every request response cycle goes through these 4 steps. If you find out on your website where you spend your time, where the delays are, that tells you what problems to go fix, right? We'll look at that in detail. But this is the basic idea, T1, T2, T3, and T4. We're going to go over them in some detail, and I wanted to address this guy's question, right? So you were saying basically that, you know, in terms of our model, T1, T2, T3, and T4, the response time should be pretty much the same as the server duration plus the network transport time.
No, it was more that I think the response time is T1, T2, T3, and T4, which is the previous sequence diagram. It seemed like it was just T1, T2, and T3.
Yeah, I didn't mark all the DNS and all that good stuff on that diagram. So that's a good point. So, what happens when you make a connection? Believe it or not, when you actually make an HTTP connection, there's a lot of work. When I went to write my book, and I just basically wrote an individual chapter for each time segment. So there's a chapter called T1, T2, T3, duh. And the T1 chapter took 60 pages. And this is before we even make a request, I was kind of dissatisfied with that. I didn't feel like somebody should have to read 60 pages of crap to figure out what the hell's going on to make a HTTP connection. But it turned out that there wasn't much that I could cut, A, because nobody had ever really explained it at that level before. Even in Ilya's book, he idealizes things and leaves a lot of things out. And the second reason that I was sort of depressed was that I felt like even after 60 pages, I could have gone on and written another 100 and had to leave them out. There's a lot going on in making connections, and this is the area in the E2E that's most neglected, most often not paid any attention to, and where you can make the biggest difference for your users. So let's have a look at what actually happens. So T1 is just the sum of the time it takes to do a DNS resolution, time it takes to do a TCP handshake, and the time it takes to establish the SSL connection, which involves yet another handshake. So 3 things. If you don't need secure connections, then the SSL term here goes to 0. Very simple. If you don't use SSL, your connections will invariably go really fast unless you have a problem. Neither one of those processes, either resolving DNS or establishing a TCP connection, takes a lot of work, doesn't involve a lot of messages, right? The TCP handshake is very simple, SYN/ACK, and there's not a lot going on there. So if you don't have SSL, T1 is not likely to be a big deal. You don't have to pay much attention to it. I rarely run into anybody that isn't using SSL that cares much about T1. The only cases where I see that is when they're having poor DNS resolution times internationally. And this often happens when companies here in the US want to move their business overseas without understanding how the infrastructure and this sort of thing works. They find they have poor DNS performance overseas. And so sometimes their T1 times are impacted, but other times, and this was sort of part of my distress when I wrote the book, is that T1 should be simple and nobody should have to worry about any of this crap, right? We haven't even sent a request yet. Let's get to the meat of it, but it's really complicated. I had to spend a lot of time going over it. The complication here is around the SSL. Right? DNS resolution is straightforward. DNS was the first NoSQL database system developed in 1983, before the word NoSQL came about. But it's actually a big flat file system that we run queries against. Sound familiar? It's typically a larger part of the E2E than most people expect. When I first started showing the people these numbers, the guys at Google in particular were very surprised at how much of a percentage of the overall E2E was spent just setting up those connections. And they went to town with that and fixed a lot of those problems. I was very happy about that, but they were surprised as well. People are often surprised. It takes longer to do this crap than you think. The other thing is that it's often highly variable, especially creating that TCP connection. What we actually see, and this is a known bug in both Apache and apparently in Nginx. I knew it was a known bug in Apache, but I just heard recently that the same bug occurs in Nginx. In some cases, when a connection is being established, if the pipe that is being used was just recently let go, you have to wait for a timer before the actual socket is released and you can talk over it. And so what we see is a big curve where most of the connections happen really quickly, and then there's some outliers for those folks who just got caught at the time when the recycling was happening. And they just got caught in a bad time in the cycle. So when you see those outliers, they aren't always something that you can or should do something about. But TCP connection times are highly variable. And like I said earlier, SSL is slow. It's just flat out slow. If you analyze why SSL is slow, there's really sort of 3 causes for this. The primary culprit is what we call OCSP, which is the online certificate, online certificate something protocol. But basically this is your revocation protocol. We make a call out to, say, VeriSign, and we say, dear VeriSign, I have this certificate in my hand, it pretends it's from Facebook. Is this really their certificate and is it valid? And then VeriSign pops back and says, yeah, I think so, or not. Right? Remember a couple weeks ago we had the big heartbeat problem, or heartbleed problem, right? Found a bug in the OpenSSL libraries, everybody went to town, everybody's up all night, typing apt install to update their OpenSSL libraries. right? When we did that, everybody had to invalidate their SSL certificates. They had to get new certificates. Very expensive to find these bugs in the OpenSSL libraries. When that happened, we immediately saw that people who had previously had OCSP entries cached, their caches were invalidated. Immediately we saw a 10x increase in OCSP traffic around SSL. SSL connections worldwide slowed to a crawl. If you go and there's a URL that I don't want to just verbalize a URL, it's not helpful to you, but if you go to X509 Labs, they have a chart of what happened during the Heartbleed massacre where they show the traffic on the OCSP providers peaking at 10 times the normal rate just because everybody updated their certificates. Right? It's OCSP to the large part that makes SSL slow. It's responsible for roughly 60% of the overall SSL connection time and roughly 40% of the variance. Right? OCSP is not a good idea, and this is why the browser manufacturers themselves have gone back and forth on it. I know you guys probably don't pay much attention to this. You're just thinking, why is SSL slow? But on OCSP, the browser manufacturers have turned it on by default, turned it off by default several times. And I think that Chrome currently, maybe, I don't know if we have anybody from Google, nobody here to check on me today. They usually send somebody. I'm not sure if Google sets OCSP checking on by default. Firefox had turned it off and swore that they will never use OCSPs ever again as of version 26. And I think we're on 29 now, is that right? So no OCSP at all in Firefox. Does that mean your SSL in Firefox is a lot faster than it is on Chrome? You're shaking your head. So you sort of shake your head, and you've been right every time until you got to this point. If you don't have to do OCSP lookups, your SSL is going to be a hell of a lot faster. I mean, this is pretty much common sense, right? And so we do see that in Firefox, SSL lookups are considerably faster in the specific versions where they've turned OCSP checking off. You can easily convince yourself of this. It's a flag in the browser, in all the browsers. If you use Firefox or IE or whatever, you can go into their options and do the same thing. Turn off revocation checking, and then go visit your favorite SSL sites. Come back and tell me whether you think OCSP makes a difference or not. Right? You'll all be lining up here to tell me how much of a big difference it makes. This is one of the experiments I do on executives when they wonder, why is Daniel banging on about that SSL thing again? Right? I'm like, let me go into your browser and turn this off for a second, and then you can surf around and come back and tell me whether you think it's a big deal or not. And they never come back and say, oh, I didn't notice anything. OCSP makes SSL slow. There's some other things that make SSL slow. Right? Simply using a 2048-bit extended validation cert is much slower than if you use a 1024-bit cert. And I'll show you data on that. It was very interesting when I saw this data. I actually measured response times for every website that takes SSL on the top 100 websites. And it was very clear in the distribution, bang, these folks are using 1024-bit keys, bang, these guys are using 2048-bit keys. So there's a big difference in performance based on the actual length of the key. And the reason for that is because SSL does asymmetric encryption for the handshake and does symmetric encryption for the block level flow. So two different kinds of encryption going on with SSL, and one of them is a lot slower than the other. Right? SSL is slow.
Typically, what fraction of T1 is TSSL?
So if you use SSL, it may dominate the response time for your entire website. If you go measure https://www.google.com, you'll find that the majority of the time is spent in the SSL, in establishing the SSL connection. It dominates. And this is, I'll show you the breakdown for the top 100 sites later, but it's either the largest term or the second largest term in the E2E for every website in the top 100 that uses SSL. SSL is slow. It's a big deal. I've been saying this for years and waving this data at people, and it wasn't until the X509 Labs folks started drawing their graphs for OCSP response times that people paid attention. So there's an interesting story there about how you can make things better on the web, right? Little old me in my little corporate environment wandered around banging on about SSL and OCSP response times for years. Nobody paid the slightest bit of attention. Hey, I'm getting paid whether you fix it or not, right? But somebody at X509 Labs, independent guy, was really upset about SSL being slow, so he actually went and measured each individual certificate provider, measured their OCSP response time, and dared to publish it. Right? Bang! Within 3 months, VeriSign's OCSP response times had dropped by half. I'm like, I'm proud of you guys. You respond to users, just not the ones that pay you. Right? Seriously, this was a perfect example of how a single individual, and it was a single person, can single-handedly change performance on the web. By publishing those graphs about the OCSP response time, this person single-handedly reduced response times for everybody on the entire internet. Boy, that must have been a great day, huh? It's like, boy, I want to wake up mornings and say I did that, you know? Why does DNS matter? So earlier somebody was saying, and it was over here, I think it might have been you, I'm not sure, so if I get it wrong, forgive me, but somebody was pointing out that before, you know, there's a lot of things that happen before the page actually gets back, right? DNS, TCP, SSL, you got to send the request, all these things, and then you get the first byte of the response time back. And in the meantime, nothing. No visual feedback to the user. You click on that link, bunch of stuff happens, your request goes off into the server, hopefully, right, into space, and eventually you may or may not get a response. And if that response comes back and, you know, slower than we thought, we may sit there and click it a couple times. Did it hear me the first time? Right? What we're seeing is the power of DNS on performance. Before the page comes back, there's a lot of the things that we need to do to get that page to come back. If that takes a long time, and if unfortunately browsers don't provide any sort of visual feedback to the user that something is happening, the user wonders if there's an error or a problem, and they click the mouse again, right? That initial chunk of the end-to-end time that takes place from the first click of the user to the first byte of the base page, not all the scripts, the images, and all that stuff that happens secondarily, that gap between the time you click and the time you get the first byte of that page back and start to see some visual feedback that something is happening is absolutely crucial. And if you can optimize that part of the E2E to the exclusion of everything else, do it. Because that's what matters to your users. They're sitting there watching the screen do nothing. And if DNS takes a long time, they might be sitting there for a long time until they go to something else. Obviously, if TCP connection or SSL connection takes a long time, the same thing is true. That initial segment, just getting those first bytes down, the initial DOM structure is the absolute 100% most crucial part of the end-to-end. If you get that right, the user will forgive you if your images take a long time to load. They're getting visual feedback, something's happening on their screen, they know something's happening, we've trained them about the worldwide wait, they know to sit there, oh, the images are coming, I just got to wait for the internet to sort of spit them out one by one, right? But they'll wait. Whereas if your DNS takes a long time, if your T1 takes a long time, and the user is sitting there staring at that screen, psychologically, because they get no visual feedback that something is happening, that's the most crucial time, the time they're likely to bail. And we've measured that many times on many different websites. The user will bail if they don't see something happening. Once they see something start to load on the screen, then they start doing a little bit of game theoretic calculation. Okay, how much time do I have invested here? Is it worth bailing? I'm going to have to go wait someplace else, you know, and they'll wait for you most of the time if they can physically see that something is happening. But if nothing is happening, they're sitting there waiting for some DNS, you know, server somewhere, then they're likely to bail. Far more likely to bail than, you know, if the delay occurs much farther down in the process. DNS really does matter. Homework assignment. So I can't have you do this little hands-on exercise in this class because A, it's going to take a little while, and B, I want you to think about it a little bit before you do it because I'm going to ask you to modify a system file. And anytime you modify a system file, what do? You think about it first. Right? Fair enough? Right? Think about it first. So, on every machine, Mac, Windows, Unix, there's a file called hosts. Usually lives in a directory called etc on Unix machines, but it lives in some other locations on Windows. It's actually in Windows System 32 drivers etc on Windows. right? But if you just search for Etsy, ETC, you will find it, right? Search is the great equalizer rather than trying to type in long path variables. So you can take that file and you can use it to eliminate your DNS lookups, right? Simply by putting the IP address for your favorite website into this host file. So go get the IP address for Google, the IP address for Twitter, and the IP address for Facebook, or pick 3 of your favorites if you don't like those. Find out what their IP address is. I'm going to leave that as an exercise to the reader. You should be able to figure out what IP addresses pretty easily, right? Put those IP addresses into your host file. Go surf. Then come back and tell me what happened. So what we've done here is we've eliminated the DNS time, right, out of T1. Right? I no longer have to do a DNS lookup. I don't have to go out and talk to my ISP's DNS server. I don't have to do anything. I just look at a little file on my machine locally, look up the IP address, I'm good to go. Right? Eliminate the DNS lookups for the web. Go do this, and then just go surf around to those websites. You will be amazed at your psychological perception, not the measurement, but the psychological perception of that initial wait while you're waiting for anything to happen while the browser is loading, right? Do this. I had a guy do this once. He was actually a very intelligent person. He's actually a vice president over at Cisco routers. At Cisco these days, he used to work at Yahoo. He was my boss. Right? He's a very smart guy, knows everything about business, forgotten more about this stuff than I ever knew, but didn't believe a word of anything that I said about DNS. And about a third of what I do is bang on about DNS, and the other 2/3 I bang on about SSL. So I was talking about it, and he did not believe me. And so I challenged him to do that, and he's like, oh, whatever, yeah, go away, got a meeting to go to. Right? So I just went in there one day while he was in his meeting and changed his host file. And didn't say anything. Right? And then I sort of made it, a point to wander in there a little bit later, because I had changed it to, our site, Yahoo, where we worked, and because I knew he surfed there all the time, and tried a couple other sites where I thought he would search. And he came back and he said, you fucked with my machine, didn't you? And that's exactly what he said. He was like, sorry for the bad language, but that's exactly what he said. And I'm like, who, me? And I'm like, yeah, I changed your host file because you wouldn't do it, and I wanted to show you what was up with DNS. And he's like, okay, I'm convinced. What do we need to do about DNS? And I said, okay, we're going to go call Dyn. We're going to go call a couple of the other vendors, and we're going to make them do a bake-off, make them give us the best performance. And that was the convincing argument. Do this little test. If you do it on your phone, I figured out how to do it on the phone. And that really made a difference. And it struck me how much DNS plays a role in mobile devices, which I had not realized before. Actually, before we get there, this is an important point since we're focusing a little bit more on mobile this week, or in this class this year. I want to point out that mobile times, we're all familiar with the idea that mobile is just slower than your WAN desktop, right? Right? I mean, we're familiar with this idea. So now we have our little model, T1, T2, T3, T4. We can ask ourselves, so what takes longer on the mobile device? I mean, it's unreasonable to think that the server itself takes longer on the mobile device. I mean, it's not the server duration, right? So that only leaves us with, the connection time and the transport time and the rendering time, right? And the transport times are probably going to be pretty heavily impacted for mobile. I mean, it's a different kind of network, right? So we can figure that T3, the network time, plays a big role. And we can probably ignore the browser rendering time for the moment because we know that, it doesn't matter which browser we use on our mobile device, it's still slow, right? It's T1. Most of the delays for mobile devices are in T1. And if you go look at Ilya Grigoryk's book, he talks about this. I'm trying to remember exactly what he says. He says something like, there's a 1,000 millisecond penalty for 3G devices and a 250 millisecond penalty for 4G devices. Don't quote me on the numbers exactly. Ilya is around here somewhere. We can ask him during the break, right? But the point is that the mobile networks impose much higher connection costs for HTTP than your desktop does. And it's a big difference. We're not talking 5%, we're not talking 10%. The T1 time segment, even for something as optimized as Google or Facebook, right? And these guys are heavily optimized. They have whole teams of really, really smart people who work, spend their whole lives focusing on this, right? Even those guys are seeing sometimes 5 times difference in the magnitude of the T1 times between mobile and desktop, right? A lot of the delay in mobile comes from that initial connection time. This is one of the reasons why I focus so much on T1. Your mobile device suffers from T1-itis in some sense, right? Server doesn't take any longer. TCP IP works the same. It doesn't care what kind of byte you are, what kind of device you're going to. Obviously, when you're going over the cell network, that's different, right? What really matters is we have to wake the radio up. We have to make a connection to the local wireless cell. The cell has to open the gateway out to the internet. And then we can go on with our normal E to E, right? But those extra steps in the mobile process are primarily around T1. If you want to make your mobile stuff faster, you're going to have to think about T1. How long does it take to make those connections? If you're doing secure connections on a mobile device, this is pretty much worst case, huh? At least for T1, right? So mobile, heavily impacted by T1. So, dig. A little tool. I'm not going to run a hands-on on it. Sometimes I do in these classes. This time I'm not. I'm just going to mention that there's a tool. It's called dig. We use it to measure DNS response times. Basically, you type dig and a domain name, and you'll get back some information about it, just like we've shown here. So here's the dig for PayPal, and you can type the command in there just like this. Just like every other Unix command, it has more options than it needs. You can look those up. But you can see PayPal has 4 individual entries in their DNS records. And this is all nice and everything. The only part that I want you to care about is this right here, 42 milliseconds. That's the time it took to actually do that DNS response time. So in the book, I spent a lot of time trying to give you an idea of what the magnitude of these things should be. And that's really hard to say. I mean, what does it mean? How long should a DNS lookup take? Right? Well, it depends on where you are and what your ISP is and how frequently that website is accessed. There's all these factors. And you might think that, you couldn't really get a good estimate, but that's not true. Right? A DNS lookup that takes longer than about 250 milliseconds is either an authoritative lookup for an obscure domain or there's a problem. Right? TDNS should not exceed 250 milliseconds anywhere in the world. And I've measured pretty remote locations to prove that. Right? So minimum time for a DNS lookup. If I use a host file on my machine, DNS takes no time at all. If I have the IP address cached locally on my laptop, then the DNS essentially takes no time at all. What if I have to go to the first stop out to my ISP? How long does that take? Well, when I measure it, it comes to about 32 milliseconds. Sometimes as low as 10, but average is about 30 milliseconds. So I'm calling that the minimum value for a DNS lookup. So somewhere between 30 milliseconds and 250 milliseconds is about right. Anything outside those boundaries, light bulb should go on. You should go, WTF, right? Normally, they take much longer and you're worrying about it. You don't really worry, if they're shorter. In this case, the DNS time was about 42 milliseconds, and from that right there, just because it was so close to the fastest possible value, you can guess that I was sitting in the PayPal headquarters when I did this test, and it was pretty much as fast as it could possibly get. Because if I go to my home, where I have very nice, fast, super optimized network, right? And I ping PayPal, I use Comcast for my ISP, and the response times are, and I know, I know this because I published an average in the book just for an example. Average response time, 72 milliseconds, more than twice this, right? And that's pretty typical of what I see in the Valley, 70 to 100 milliseconds for a DNS lookup, just to give you an idea of what these things should be. Remember the thing about personal experience, right? Understanding, being able to look at these numbers and understand, boy, that's really low. How did it get that good? Or boy, that's really high. What's wrong? Is really helpful. Use Dig to measure your response times. There's other tools you can use. That's my favorite. So that's it for T1. And I've spent a lot of time talking about T1, and most people would have not mentioned anything other than, you know, we got to make a connection and move on. It's a huge performance factor. I don't want you to neglect this. In fact, when we go back later and measure a website, we're going to say, what percentage of the response time is in T1? How much of it is in T2, T3, T4? We're going to go figure that out. And what it's going to come back is that for any site that uses SSL, T1 will be the largest time segment, unless you're streaming video or something, right? Very important to focus on anything you can do to optimize T1. Unfortunately, T1 is all about the network. Fixing it might be expensive, might require you to make network changes, might require you to go and arm wrestle with your ISP and say, look, these DNS times are unacceptable, and your competitor is right over here. He's got better response times. Right? It's not as simple as going and fixing a piece of code to optimize T1, but it's well worth doing. It impacts every user, not just the few. T2 is the server duration. This is the part where most of the people want to focus most of their time on optimization, because most of the time they're developers. Right? And they write the code, it lives on the server. This is the part that they personally are responsible for. Now, as performance experts, we know not to get involved in keyhole optimization, right? So server duration is not the whole thing. We learned that earlier, right? But it is important. There's no question that, you know, if the server didn't take any time at all, things would be faster. In fact, for most HTTP requests, the server duration is essentially 0. This is true everywhere on the web. All right, so you're looking at me like I'm crazy, and that's cool because it was a crazy statement, but it's true. Why? So server duration is mostly 0 for requests on the internet, or near 0. It's not exactly 0, but it's minimal, few milliseconds at most. Why is that? And you're sitting there thinking, well, my machine takes, or my company takes, you know, 4 seconds to get that database query back, right? How can it be that most server duration don't take any time at all, or very minimal time? Well, come on. What are the majority of the requests for? Static files from the CDN, GIFs, scripts, all this good stuff. How much smarts does it take the server to send a script? It's a flat file. Servers, I mean, by definition, this is what a server does, is it takes a file and shoves it out over the wire, right? If they're optimized for anything, got to be optimized for that. In most cases on the web, the server duration, if you just go and look at a per request basis, the server duration is essentially 0, right? Very few milliseconds to stat that file into that socket, right? Does that mean that T2 isn't important? Hell no. It's very, very, very important, because the 1 or 2 cases where the server actually does work are the ones that are important to the user. Right? Those GIFs and scripts may not be terribly important. I mean, they look nice and everything, but if, you know, the login box and the submit button don't come up, right? It's like, I don't care about the images, right? So once again, I think about this multi-step process I go through to load a base page. I load a web page. I load the base page. I get that DOM structure. I go out to the CDN. I grab scripts and images and all this good stuff. At some point, the page calls time. Maybe it cries uncle. And then we go into our third phase, which is our deferred loading phase. After the page loads, we feel like we're free to go and make some additional calls. We might call ads. We might call counters. We might call performance measurements. This is our third phase. 3 phases to loading a web page in 2014. Get the base page, get the intransitive hyperlinks. Those are the ones that identify those static assets, scripts and GIFs and so on. And then we go through a deferred loading cycle where we load things like ads and beacons and this sort of stuff. right? That deferred loading cycle is designed so it doesn't impact the user experience, right? Page's already done loading, what do you care, right? You're busy using your think time, reading whatever it was that came back on the screen. Meanwhile, the web page very cleverly is taking advantage of the fact that you're distracted reading the screen, and it's sending off all kinds of stuff and measuring it, right? There's some cases where that doesn't work. Once again, to pick on my favorite employer, right? At PayPal, we have this sequence where you go through login, review, confirm, right? We don't want you to spend any think time on that. We want you to go as fast as possible. But the ad that we loaded at the bottom of the page never comes up, right? Because, hey, we moved from one page to another too quickly for it to come up. So we defeated our own deferred loading strategy and had to think up something else. But so it's not in every case that those three phases work. And like I said, in that second phase where we're accessing those static objects on the CDN, the server duration near zero, minimal, whatever it takes to stat a file. Remember, statting a file does not depend on how big it is either, right? It's like you can stat a big file just as fast as you can stat a small file, right? So the only place where T2 matters, when you are downloading that base page to get the DOM. Right, so you made a request, that's where T2 began, right? We made a connection, T1 ended, now we've got a connection, the server is going to answer our request, now we're on T2, we send a request, and we sit and wait for the first byte of the response to come back. T2 ends when the first byte of the response comes back, right? And we call that the amount of time it took the server to do its thinking. Now, there's a little bit more than that. Obviously, it's the time it took the server to do its thinking plus the time it took at least one packet to come from the server back to my client, right? Because I got to get that first byte of the response back. But, you know, to first order approximation, that time is the server duration between the time that the connection is made and the time that the first byte comes back, right? So when we make our call to the base page, so let's pick on Google again. Seems like I'm picking on them a lot today. Maybe I should pick on somebody else. But okay, let's pick on Facebook. So Facebook goes out and you type in www.facebook.com and it comes back. You made the connection, whatever it took, SSL or not, and so forth. Then you send your request, you know, get index.html from Facebook, right? That's the base page. That page comes back and the browser sucks it into memory, so removes all those intransitive hyperlinks. The intransitive hyperlinks are the ones the browser clicks on for you, rather than you clicking on yourself. Those are called transitive hyperlinks. Intransitive ones are the ones the browser clicks on for you, on your behalf, right? Associated content is the actual formal term. Page requisites is something, you hear that as well sometimes. The browser hauls back that base page from Facebook and it says, you know, HTML, body, head, whatever it says inside there. The browser takes all that, sucks the data out, and then starts making those queries and starts that second phase, right? That time it took the browser to think about what HTML to send, or took the server, pardon me, to send that HTML to your browser is the server duration, and it's the part of the request that matters to the user. If no images ever show up, it's okay. I mean, seriously, if we took all the pages off of Google, would you really notice? I mean, okay, so you wouldn't get to see the cool logo now and then, but otherwise, right, the page will work fine, right? But if that base page had not come back and we were not able to read that, it would have failed. And it took Google server, Facebook server, Twitter server some time to figure out what page to send me. Normally what happens, request comes into, say, Facebook server. It goes and gets a basic template, looks you up, right, and says, oh, Chip, come back on Facebook, huh? Time to waste more time. And, oh, but I know you, so I'm going to make this, this page special for you, and I'm going to go and look up all your, you know, the stuff on your wall and all your recent likes and all the updates from your buddies and all the good stuff. And that's going to take some time. Right? Because I got to go talk to the database, I got to go talk to the messaging system, and I got to write some log files, and you know, there's some complicated stuff going on back behind there. It's like anybody that's ever worked in a large-scale web shop knows the level of complication that goes on back there is really amazing, right? It's like it's not simple. It's like you would just think, oh, a redirect. Something as simple as a redirect might have a team of 6 people working on it. Yeah, there's really teams of 6 people out there working on redirects. The important point is that that base page is the one that matters to the user, right? Those scripts and so on, secondary in importance, right? So the only point where T2 matters is when you call Facebook itself, not when you call Akamai, not when you call Amazon, when you call Facebook.com. The server has to think about it a little while, and then it spits out, you know, Chip's Facebook page or my Facebook page. Those are very different pages. Boy, are they different pages, since I haven't been on Facebook in like 2 years because I have no time. But everybody's page is different, and the amount of time it takes to compose that page, the page composition process, is often very lengthy, right? So I have a question for you. So I derived the response time law here. Don't worry about it, right? Simply ignore all that mathematics, because I'm going to ask you a question, and you're going to look at me like I'm cross-eyed, or like you're cross-eyed maybe. So Chip's going to Facebook. He's going to drag down his base page. We're going to ignore all those images and all that crap for the moment, right? Just going to drag down the base page, and he's going to do that several different times, right? And he's going to get a different number each time, right? If you make the same request to the same server from the same location at roughly the same time, you would expect to get roughly the same result back, right? But if he requests his Facebook page 10 times in a row, remember we did this with DNS earlier, right? He's going to get wildly different results each time, right? So the first question that I have for you is, why is T2 not constant? Shouldn't it be constant? Make same request from the same place to the same server at the same time, and I get different results. It should be a constant. Duh, damn. Yes, sir? Okay, so ignoring caching, but that's a very good point. We'll see the results of caching in a moment, but independent of caching, right? You were next.
Server does have resource limits, so it really depends on the capacity of the server too.
Okay, and that's totally right. Just like I was talking earlier about the secular cycles, right? At noon, there's a lot less capacity than there is at midnight, right? So we might expect that servers would actually be faster at midnight. They are. Right? So there are some differences in the capacity of the machine. So if he asks for his Facebook page at midnight, I might expect it to be a bit faster than it would be if he asked for it at noon. But if he makes 2 requests at noon, right, one after each other, bang, bang, then I would expect at least, you know, so the network may be having something going on or whatever, but I would expect at least the server duration to be constant. Right? If I make the same request to the same server from the same location at the same time twice, I should get the same result. Why isn't T2 constant? Why do we care about T2 at all? Right? I mean, it's 0 for static files, and it should be a constant, right, for most of the time. Right? So why do I even care? But I do, and it's the first thing anytime anybody says performance optimization, they run and hug the server. Does that make sense? So it does to a certain extent, but not to as much as you would think. So here's the key to this. The first one is the point that this gentleman brought up, right? As the server gets more and more busy, the slower it gets. Remember, we talked earlier, one of our goals is we wanted our costs to scale linearly with the number of users, right? We'd like response times to scale linearly with the number of users too, right? A busy system is going to be slower than a non-busy system. This is just the force flow law. You can't change that. This is underlying physics. What you can do is make sure that as the number of users coming into your system increases, the response time does not start to weigh down, right? You do that by adding capacity, right? I mean, it's very simple. What Netflix does, just to give you an insight, so Netflix, everybody knows they're all running in AWS. Right, so they use rack space and some other stuff. I hope I'm not giving away too many of their secrets. I don't work there, so they can't sue me. But for most practical purposes, they're in AWS, and of course they can whip servers in and out pretty quickly. Right, so between 15 and 30 seconds is what they told me to be able to add up to 1,000 servers. Right, that's pretty remarkable. Boy, I couldn't have done that 10 years ago with 1,000 people. right? Literally could not have done that. So very remarkable. And AWS and the large cloud systems are themselves very remarkable systems. But what the Amazon guys do is they automatically increase their capacity at peak times. They know what their peak times are. They just look at their log files and see when the most people come in. They just throw a lot more machines in to counteract it, right? And it works pretty well. They have reasonably linear response times regardless of how many people are using the system. And that's what we want. We don't want it to be the case where what's your name? Huh? Paul. We don't want this guy to be coming in and, getting a really good deal, good response time at 11 o'clock, and then he comes back at noon to check his email and it takes twice as long, right? He's like immediately decided that he likes other email providers better, right? And who can blame him, right? Unpredictable, unreliable response time, right? So what do? You add more capacity so that at lunch, even though you're busier, right? His email comes in reasonably close to the same response time as when there were fewer people on the system, right? Congested systems are going to be slower. There's no stopping this. You can't change this, right? When more cars get on the freeway, they're going to move more slowly, right? It's just, this is, the underlying physics of the situation. But what we see happening is that systems often go non-linear at peak time. And that's what happened here. So this is a Yahoo server. And the green line is the CPU. Red line is the number of milliseconds of response time for an HTTP request, right? This is time in milliseconds. This is the number of users. So what do you think happened? So things were fine up to here, huh? Let's just look at the response time. Ignore the green line for the moment. And let's just take a look at response time. Performance is response time. We don't care about, CPU utilization. If that's high, go buy another CPU, right? We care about response time. And everything was pretty fine up to here. So as the number of users on the system increased, this slowly increased, but it looks more or less reasonably linear, right? I mean, nothing is straight in the real world, but it looks like this system was scaling reasonably, right? And then we got to the magic number here. So we had about 10 users. Then we got to the magic number of about 20 users. And what happened?
That's sporadic.
So anybody that works at one of these places will know what this means. The server started flapping. Everybody knows what that means? Yeah. So you start seeing highly variable response times going like that. And that's exactly what we're seeing here. So if he comes in to this website and he comes in here, say he's user number 18, his response time is not going to be very different from user 15 or user 10, right? But if he comes in, he's user 25, right? Suddenly the whole thing has gone nonlinear and his response time is a lot higher than it would have been if he had only been user 18, right? And you can see that it just went haywire and basically the users gave up at that point, right? You can see the number of users do not increase past that point. If they had, the response time would have gone down and down and down, and eventually the server would have stopped. Servers will stop when they become too overloaded, right? And I mean, if you let a server in a commercial environment get to that state, you need a spanking, but they will stop and freeze up. And normally what happens is you get some huge spike in traffic, right? So when Michael Jackson died, Yahoo fell over. Anybody remember this? So Yahoo just fell over, bing, flat on our face. And we were embarrassed. I mean, we had egg on our face. We thought, we were the best damn website in the whole friggin' world. How in the world can we go down just because some idiot with bad hair dies? It's like, no, we were very unhappy with ourselves. So we went and reworked the entire availability of all of Yahoo's website, built our own proxy system, built our own CDN, created our own DNS system, and created policies for taking all the ads and images off of pages anytime somebody dies, right? So, no, seriously, and it all works now. And what we saw when we did that was linear scaling responses up to 100x of normal traffic, which is damned remarkable. 2 orders of magnitude scaling with linear response times, right? But we had to move heaven and earth to do it, and it cost more money than most websites cost to begin with, right? The point here that I want to make is the relationship. Once again, we're ignoring the response time law because we went over it earlier. Remember likes in Facebook and how long they take? This is exactly the same thing, right? You got a lot of people in line. It takes them a while to get through the queue. Right? So you can ignore the math. I put it on here because in another class where I use this slide, I go into more detail explaining it. The important thing that you want to know is that you want T2 to scale linearly with the number of users. Right? Whatever it takes to make that happen is good. If you fail to do that, your system will fail. Right? I mean, there's just no other way to put it. I can't put it nicely or you know, any syntactic sugar associated with it, right? If you start going nonlinear, your choices are take the traffic and put it on another machine, turn that machine off. Right? Because once it's gone nonlinear, it's over. Right? And you can kind of see that. Some of these folks, right, came in and got reasonably good response times. Other folks got something crazy. What you see when things get congested, when they go nonlinear, isn't necessarily that every single user gets a slow response. It's that the users start getting highly variable responses, and you have no idea how long it's going to take that user to get their response, right? If this wasn't flapping, let's say that this is all nice and linear. Well, you can see that, you know, these folks down here in these data points, they saw pretty much the same performance the earlier folks did. The folks represented by these data points were going exponential, right? So what we see is some users got a good deal and some users got a bad one, right? It wasn't everybody suddenly gets a bad deal as soon as you hit your linear scaling limit. It's that now response times have gone extremely variable. You have no idea what's going to happen until the system falls over. And you know that that will happen once you've gone nonlinear. So I'm going to stop here for a second just because I want to, it is a little bit complicated here. Most people don't spend a lot of time thinking about their servers in this way. They want to go fix their code, which is always good. But I want to stop for a second and see if we got any questions on T1 or T2. Sir?
What do the two different lines on this graph represent?
Oh, so the green one is CPU utilization. And the red one is response time. So remember that this is the number of users. As it goes up, my CPU gets used more and more. Now, I'm not quite sure what your question is, but a question I get about this sometimes is, so the CPU went nonlinear there, but the response time went nonlinear before that. How come? Which is a good question. Do you see that? So we've got two curves, and they both have some point where they go nonlinear, right? But they're not the same point. And you would think that the CPU would go nuts, and then the user's response time would go nuts as a result of that. But what we actually see here is that the user response time went nuts, and the CPU was still scaling pretty linearly at that point. So what happened?
So basically, the congestion happened before the CPU reaches its capacity.
So it's not the CPU, right? I mean, that's basically what the graph was telling. And when I first made this graph, I didn't make this graph for this this presentation or whatever. I was actually trying to diagnose a problem and later pick this image up as an example. What I was trying to find out was what was causing the nonlinear response times. And what it turns out was that for this particular operation, there was a lot of memory being used, and we ran out of memory about here, right? But it might very well have been we ran out of disk or we started swapping, right? The network number of connections became saturated, right? There's any number of different things that can constrain a system, right? We normally think about CPU, RAM, and disk as, you know, the canonical three, add a fourth one, network to that, and whatever's constraining your system is going to be one of those four things. Either that or you've got some weird unicorn case, right? But in most cases, right, it's disk, CPU, or RAM. And for most web pages, CPU is not an issue. So this is probably a useful little bit of insight. So if we think about RAM, network, CPU, and disk, what do you think is going to be the most critical for web pages? And I just told you it was the CPU. So, RAM. I got some votes for RAM over here. Anybody else?
Disk also is a
Disk? Huh? RAM? So I've got RAM and I've got CPU. I heard one call for disk. Nobody said anything about the network. So here's another question for you. Is the internet network bound? The constraining factor on response time in the network is not the response time of the server. It's the response time of the network. There's plenty of RAM out there. There's so much CPUs out there sitting there bored that, you know, we could sell those CPUs for a dime a piece on eBay and nobody would notice because they're not being used in those servers. You could just take the chip out half the time, right? It's not disk. I mean, seriously, it's like if we've got disk problems in 2014, you know, we need to hire somebody else, right? Because disk is cheap and reliable and basically a commodity at this point, right? So could be RAM, could be CPU, could be disk, could be the network. It's not the CPU. Most web pages are not CPU intensive. There's just not a lot of calculation going on. It's not likely to be RAM unless you're actually using Java or something that some virtualized programming language, you know, that wants to suck up a specific pool of RAM and a fixed way, right? That's bad behavior, by the way. And I told them that when they were developing Java, but nobody listened. We know that it's not disk because, you know, static files on disk isn't the big deal. So that only leaves the network, right? The web is largely slow because of the network. If it ran on machines in your closet, everything would be very, very fast. The internet is network bound. It's something most people don't realize. Be that as it may, the server duration can go nonlinear for any number of reasons, not just because of the CPU. And that's kind of, did that answer your question? Did that address? I was trying to reach in and understand what you were asking. This is the number of users. This is the response time, milliseconds. Right? So here at 20 users, I'm seeing 200 millisecond response time. 30, I'm seeing 300 millisecond response time. So the graph is rotated. You're used to seeing it with the dependent variable on the y-axis. Didn't get drawn that way this time. Developer pumped it out of RRD tool or something. Anybody know or use RRD tool? Really?
In my experience, most frequently see something like that because of a memory leak.
For a memory leak, that definitely could cause it. So the gentleman said that in his experience, he often sees the system going nonlinear like this due to memory leaks, and that's exactly right. Out of those three parts of the machine, essentially disk, RAM, and CPU, right? The RAM is the one that actually has the smallest capacity, most likely to start flapping, right? And also the one where memory leaks. So a memory leak basically is another way of saying that we didn't manage our memory correctly and release it to other applications, right? So what we really got is some greedy application that's causing all the other applications to suffer nonlinear response time. Sounds like keyhole anti-pattern, right? That selfish application, spank. You're still looking quizzical. Is that just because it's rotated? I'll redraw it and rotate it.
There's different values of response time in the same group.
So why would that happen? Oh, that never happens. So why would that happen?
For a given number of users, there be one response time.
Well, that's pretty much the same question as if I test Twitter 10 times at the same time, shouldn't I get the same response time? Isn't that exactly the same problem? but you just tested Twitter 10 times and you know it didn't come out that way. So your intuition is exactly right. I would like that to be a constant value, right? That's what I was asking earlier. Why is it not constant? Why do two users see different response times even if they're number 20 or number 21 in the system? And let's just say, you know, it goes nonlinear at 20. Why is that? So for just the server duration, the reason that that happens is because each individual request at the time that it goes in will find different levels of queue residence times while it's waiting for resources, right? If RAM is really busy, the queue residence time to access RAM will be longer than the queue residence time to access the CPU. But some users in the queue will actually get both good response or good access to memory and good access to CPU. They'll get good response times. These other folks are waiting in line back there for the memory chip, right? Largely because somebody else's app has leaked and taken away the memory that they could have been used, so they didn't have to stand in line. But it's a good question. Why is there so much variability around this stuff? Can't we get to some point where if I measure something, I can go and measure it again and get the same result? I mean, that whole science thing was like reproducible and verifiable and all that, right? What happened? Well, it is. The problem that we have here is we're taking individual spot measurements, right? If we looked at 10,000 servers and we do the statistics, everything will be nice and smooth and just the way that you think. In this particular case, some users, these ones up here, got a really bad time, and you can start to see the exponential curve forming here. Well, these guys were still linear, even though the same number of users were on the system at that time. One thing you might think about if you were actually going to analyze this and solve it to figure it out, are these widths periodic? Are they about the same? Is there some cyclical thing happening here? Right? What's really happening, I think, is that you're swapping. Right? And there's a certain fixed size of swap out to the disk. But anyway, I want to stop and see if there's questions about T2 before we go to lunch. Because we were supposed to go to lunch. Okay, everybody's sort of sitting there and their eyes are starting to glaze a little bit and having trouble breathing. It's like, okay, I promise no more statistics, don't go away. No, more seriously, I just want to make sure that up to this point, people have a grip on what we're talking about. Second half of the talk today, we're going to do T3 and T4. That's very exciting, I know, after talking about T1 and T2. Yeah, I know, I'm just kidding. We're going to go and measure some web pages and learn how to use tools like CompuWare and Keynote and some other things. We're going to learn how to use webpagetest.org. We're going to learn how to read waterfall diagrams, because beyond putting your hands on the numbers, reading waterfall diagrams is one of the key skills for performance people. And by the time you leave here, I want you to be able to stand back there where that water cooler is and look at a waterfall diagram up here on the screen without being able to read anything on it and tell me what's wrong with that web page. And you'll be able to do that by the time we leave today. Reading waterfall diagrams is a key skill, and that's what we're going to cover very shortly. Last thing that we're going to talk about, mobile and HTML5, a little bit later in the day, and then we're going to wrap it up. But before we move on, I want to see questions, thoughts, comments. Am I boring the crap out of you yet? Okay, thanks for that. Yeah. All right, so we're going to stop here and start again after lunch with T3. Comes right after T2, right after.